Hey everybody, Mrs. Derby here. Sorry I'm not there. I want to get you going on. It's Thursday, so we're going to do our Thursday bell ringer. We're going to do a handout here like this. It's a little half-page handout, so grab that from the pickup station. And we're going to work on parts of lesson 15 in our workbook. So you'll need all of those things plus a calculator. So if you need to, hit pause right now, gather the stuff that you need. I'm grabbing my calculator, so I'm also set to go. And when you're ready, hit play again, and we're going to see what we've got going on with these things. All right. Today, our big focus, lesson 15, is thinking about percent change. Okay, so we've seen some examples of this already. Today, we're just going to make it deliberate. That's all. So we're going to start with our bell ringer, go to some percentages, and then see how we would do something in our lesson 15 workbook. Follow along with me, pause if you need to, and make sure that you're taking good notes because you are capable of learning from a video. It might just take once or twice or pausing and thinking about it. Okay, let's read Thursday's prompt. A person has $1,200 in their bank account. It doubles, that means times 2, each decade. Now, a decade is 10 years, so that's just a good thing to know. Write a function to describe how much money will be in their bank account after X decades. All right, so this is something that we have done a couple times, writing an equation to model a situation. My answer for that would be that I would start with the $1,200 in the bank account. I don't know why I wrote my 2 first, but I did. It is doubling, and it's doing that for every X number of decades. Now, what that's going to do is it's going to tell me the account balance. So I'm going to say that all of that equals the balance on the account. So now I need to use my function to figure out how much money will be in the account after 4 decades. Take that 1,200, we're going to double it 4 times over. Now that means 40 years, so be careful with that. That's 4 decades. 1 decade equals 10 years. That's a good thing to start knowing. We're going to start doing some time span changing like that. And so I just need a calculator now. That's going to let me solve this answer really quickly. Just typing it in, just like I wrote it. 2 in parentheses, raise it up to the 4th power, hit enter. And if we can really double our money every 10 years, this $1,200 investment ends up being $19,000, $19,200. So that's a really good rate of return right there. If I just put $1,200 in a bank account and let it sit there and just keep on doubling, and I can do that for 40 years, that's a really nice return. This is how people retire, and they generally say nowadays, I guess, that you should have like $1 million in your retirement account. You don't put in $1 million. You put in a little bit, you put in way less than that really early when you're young, and you let it grow for a long time. When you're set with that, turn your attention to this page. I'm just going to do the first part of it and then ask that you pause the video in order to see if you have it on your own. Okay, so we're looking at percent change. Now careful, because there's 2 sides to this and they look very similar, but I'm starting on the side that has your name at the top. So go ahead and put your name up there, what hour you're hanging out here in Algebra 1. And the difference is that on the front side, we're talking about percent growth. Okay, so if we're talking about percent, and we know growth has a factor that is greater than 1. Okay, we've said this many times in class already, that for something to be growing, it has to multiply by something greater than 1. So our percent growth if we know how it's growing, we're going to add that percent to 100. So we're going to start with 100. We get to keep 100% of what we have. And then we're going to add that growth on top of it to get a percent over 100. And then to change that percent to a decimal, we would move the decimal point 2 spots to the left. So you see how this says 103.8. I would move that once and twice so that it's right there between the 1 and the 0. And I would get 1.038. And that is our growth factor for the equation. So this is again showing that I'm keeping the 100%. I keep everything. And you remember that growth factors are keeper values. How much are we keeping? And then this is what is growing on top of that. So that's the percent that it's growing. Okay, and that's how we put it into a decimal. And that's what we would use if something was growing at 3.8%, say, per year. We could have that kind of growth with this multiplier. Let's do it again. Start with 100%. If this is growth, this 4.1 is on top of that 100%. So that's 104.1. That's the percentage. Move it 2 decimal points, and it's 1.041. That would be our growth factor that we would use in an equation. So you could probably start doing some of this like in your head, right? If I add 100 to 2.9%, that's 102.9%. Move that decimal point 2 places, 1.029. Some of these might look a little tricky, right? When we start getting to some of the double digit, right? So 100 plus 12.7% is 112.7. Still the same thing. We're going to move that decimal point 2 places, 1.127. It also looks a little tricky sometimes if we're adding a decimal of a percentage, not even a full 1%. This is now 100% plus 0.56. That is 100.56%. Move that decimal point 2 places, 1.0056. And there we go. Now this one looks like it just printed off with an extra decimal point in front. So that is not the decimal point. It's 2.19%. Keep on filling out the rest of this. I'm going to do a couple examples on the back side. And then you should hit pause to finish off this paper. On the back side is the percent decay. So it's telling us we're going to subtract the percent change from 100. Remember, if it's losing value, we always want to think about how much does it keep to write in our equation. Okay, so our percent decay is going to be a factor that's less than 1 to show that it's going down. It's losing value. And so here, that's exactly what they do. They subtract 3.8 from 100. They get a number that's less, a percent that's less than 100%, because it's keeping 96.2%. That means it's losing, right? This is the amount that it loses. Think about that, okay? This is the amount that it loses. This ends up being the percent that it keeps. We always write our equations based on how much value it keeps. So they do that math here. And again, they move that decimal point 2 places. And we end up with a decimal point that is less than 1 because our factor is showing decay. 100 minus 4.1. I have to admit, I'm not good at mental subtraction. 100 minus 4 is 96. And I need to subtract another tenth. So that would be 95.9%. No shame in that game if you need to use your calculator for this part. Sometimes I still do too, just to make sure I got it right. And then I'm going to move that decimal places 2 times. Decimal point moves 2 times. The reason why we do that, why we move it 2 times, is because per cent literally means per 100. So what we're doing is 95.9 per 100. Okay, that's per cent, because cent means 100. There's 100 pennies in a dollar, 100 cents in a dollar. A century is 100 years. And so if we did that division by 100, we'd end up with this decimal point. And we can keep on doing this. Like if I have 100 minus 12.7, $87.3 is how much it keeps. So it loses 12.7. This is the keeper amount. Move that 2 decimal places or divide it by 100. And we find out the multiplier that we would use in an equation. And we can see that if it loses something very tiny, like 0.56%, we're still going to have something like 99.44. Move that 2 decimal places. We find that multiplier factor. Hit pause. Give yourself 5 minutes or so. Complete the entire sheet. Get that practice. Okay. When you're ready, hit play again and we'll do lesson 15. Lesson 15, and we are going to just take a quick look at 15.1, dandy discounts, because this is a question that a lot of people ask me. They're like, hey, Mrs. Derby, if I go to like a store and I've got a 50% off coupon, and I've got another thing with another 50% off, do I get the thing for free? And you don't. It'd be really cool if you did. Okay, but let's figure out why that's happening. All books at a bookstore are 25% off. Priya is buying a book that was originally priced at $32. The cashier applied a store-wide discount of 25% and then took another 25% off for a coupon that she bought. And we're going to say there's no sales tax. We want to see how much she pays for the book. Now, a lot of people think that if I'm getting 25% off from one coupon and then 25% off from another coupon, then it would be 50% off. So I'm going to put that question here. I'm going to be like 50% off. Is it half price? Because that's what a lot of people think. Let's do it one discount at a time. If we start with $32, and remember, this is the discount price. So this is how much it loses. Okay, so if it loses 25% of its value, we're going to do 100 minus 25. 100, this is our discount. 75% is how much of its value it keeps. Okay, so this is the store-wide discount. That 75%, move it 2 decimal places, is 0.75. So 32 times 0.75, there's our factor. This is what it's going to look like after the store-wide discount. Oop, I put 25. Ugh, not thinking. $32.75. I knew because I thought, wow, that's a lot of money. That's more than half. So it's $8 off. We could subtract that from 32, or we could just do this times 0.75, do it the right way. And we find that it's now going to be $24. And then she has another coupon that is also 25% off. So that means it keeps another 75% of its value. Remember, it's a keeper, okay? So this is the store-wide discount. This is now going to apply her coupon. 24 times 0.75 again. Now is $18. That's how much she would pay. Now it's not half off, because 32 divided by 2 would have been $16. She's paying $18. So it's close to half off, but not fully all the way half off. Okay. What she did is she got $8 off, and then she got another $6 off. Okay. So again, it's not the same number that each of the same factors does. It's a consistent factor. So let's see how this works. There's this thing about owing interest. Credit cards love doing this to you. Okay. To get a new computer, a recent college graduate obtains a loan of $450. She agrees to pay 18% annual interest, which will apply to any money that she still owes. And let's say she doesn't make any payments for the first year. Okay. Now this annual interest is still saying that she still owes the full 100% of what she borrowed. She owes the full $450 plus 18% interest. So what it ends up being, if she owes the full 100% plus 18% interest on top of that, is 118%. Okay, so this is one of those things that we're looking at growth. The amount that she owes is growing. At the end of 1 year, her $450 that her loan started at, still a starting number. I'm going to multiply it by 1.18 because that is 118%, rewritten as a decimal multiplier factor. And if we do it at the end of 1 year, 450 times 1.18 means that 1 year without any payments, she's going to owe $531. Okay, so annual, remember, means 1 year. Assume she continues to make no payments to the lender. How much will she owe at the end of 2 years? Or how about 3 years? Well, that same $450 with 1.18 interest, 18% interest on top of what she owes, right? She's not making any payments on this. Now the next year, it's taking that same 18% and adding it to a bigger number. So the loan is going to grow even more than just this $81. Okay. So if it's the end of 2 years, we're going to bring it up to the second power. 450 times 1.18 up to the second power, $626.58. That means in the first year it was $81 extra. Now it's $95 extra. Guess what? She's going to owe more than that for the next year too. So for year 3, 450, 1.18 to the third power, $739.36. All of a sudden this computer, that she paid $450 for, only 3 years later, if she doesn't start paying it off, it's going to be a lot more expensive. Okay. So they then explain it here in step 3 to find the amount owed at the end of the 3rd year. Somebody said, well, hey, the year 3 amount is the year 2 amount plus that amount times 118, and ended up with this kind of thing over and over again, which is exactly what we did. The year 3 amount is $450 times 1.18 for the first year, times 1.18 for the 2nd year, times 1.18 for the 3rd year. We multiplied that 3 times over, so this is a shorter way to write it. Does our final expression correctly reflect the amount owed at the end of the 3rd year? Yes. This is the starting value of the loan. This is the multiplier factor. And it multiplies by the number of years that she's gone. So at the end of any X number of years, if she doesn't ever pay this thing off, this is how people get into credit card debt and like real trouble, is that it keeps on building and building and building. They buy something, they think they're going to pay it off. They don't have enough money to pay it off at the end of the month. It starts accruing interest. It starts gaining interest. It adds to the loan. And so you have to pay that money off on their schedule. And if you miss that schedule, they charge you a higher interest for the next month. And it can keep on doing that over and over again. Pay your bills. That's my tip. All right, 15.2 is all set. If you need to, pause something, ask the person next to you, see if they can help you out. But we're going to look on 15.3 to see about comparing loans. Okay. So when you're ready, hit pause and then play to go on to 15.3. Suppose 3 people have taken out loans of $1,000, but they each pay different annual interest rates. This is so true, right? Everybody has what's called a credit score. They check how well you pay your bills on time and the full amount that you're supposed to pay. And if you are a risky person, like if you don't pay on time or you don't pay the full amount, they're going to charge you more in annual interest rates because they want to make sure their money is safe and protected. So one person gets a 12% loan, one person gets a 24% loan, and one person gets a 30.6% loan. Okay, so this person has the best credit score because they have the lowest percent. This is what's added on as interest. Okay, so if you're adding interest to a loan, you want it as low as possible. We'll talk about savings accounts soon. All right, for each loan, write an expression using only multiplication for the amount owed at the end of each year if no payments are made. Okay, loan A starts with $1,000. They're still going to owe that $1,000 loan, but then also add 12% on top. 100% plus 12% on top of that is 112%. That's 1.12. I'm going to stick with this loan. If I want to do that for 2 years, this one just says write an expression. It doesn't say to actually calculate, okay? So I'm just going to keep that in mind. Same loan after 2 years. Same loan after 3 years. Same loan after 10 years. And then we can, of course, do that for any number of years. It says to use graphing technology to plot the graphs at the account balances. Did it really ask us to calculate each loan for the amount owed? I guess maybe they're asking for us to actually calculate it. I guess they're asking for us to actually calculate it. I'll do that better with these over here. All right, so 1,000, 1.12. This person owes, after 1 year, $1,120. After 2 years, we're just going to multiply that by 1.12 again. And that becomes 1254.4 cents. In year 3, we need to multiply 1.12 again. I'm going to round it to 2 decimal places because it's money. And now I'm going to calculate this because it jumps to 10 years. So if this person makes no payments, their $1,000 loan 10 years later is more than triple. And that's the person with the best loan rate. Loan B, I'm going to go ahead and just write its function up here, or I guess maybe down here. That $1,000, this time at a 24% loan, that's 100%. They still owe the full amount plus 24% on top of that every single year. That's 124%, or 1.24, raising it up to the x power. Let's calculate and write down some values. 1,000, 1.24. After 1 year, it's 1,240 times 1.24 again. At the end of year 2, $1,537.60 times 1.24 again, $1,906.62. And then after 10 years, 1,000 times 1.24, raising it up to the 10th power. This person owes, oh my gosh, $8,594. Do you see the difference in those two loan amounts? And that's only based on the percent that they're getting, right? The percent they're being charged by whoever gave them this loan. That's a huge difference. This person's has tripled. This person's is 8.5 times bigger. They owe $8,500 on a $1,000 loan. This is the power of what we call compounding interest. It keeps getting bigger and bigger and bigger. Now, loan C, same kind of thing, 100% plus 30.6% on top of that. That's 1.306 as our multiplier. So this $1,000 loan, 1.306 to whatever power we're going to be looking at. That $1,000, 1.306, $1,306 times 1.306 again, times 1.306 again, and then to the 10th power. This poor person who is stuck with this 30% loan for 10 years, $14,435.50. Friends, this is how people rip you off, okay? You should never, ever, ever take $1,000 loan and have to pay back 30% interest because look, even in the first year, if it takes you 1 year to pay off $1,000, you're paying an extra $300 just to borrow money from somebody. And if you don't ever pay it off for 10 years, they will let it get up to $14,000 and then send you to collections where they track you down and they take money from your paycheck. And they're allowed to do that because you signed a loan that you promised to pay it back. And if you don't pay it back, they will come get every bit of their $14,000 because they feel like they're owed it. All right. It asks us to use graphing technology to plot the graphs. And then based on our graph, how many years would it take the original unpaid balance of each loan to double? Okay, so we're going to go loan A, loan B, loan C. We're looking for where the Y value doubles. So if it starts at $1,000, we want to know when it's going to hit $2,000 of value. Now, I can already tell in loan A, it's somewhere between 3 and 10 years because this is under 2,000 and this is over. Okay, same thing here, and it's going to be probably shortly after year 3. Loan C, it is somewhere in year 2. Okay, because $2,000 is somewhere in between this 1705 and this 227. So I already know that loan C is between year 2 and 3. It does not take long for that to double. So I'm going to go to I think I can go to this screen. Oh, there we go, maybe. I'm going to open up a Desmos. And I can type in my equation over here. So this is loan A. Yeah. A of X. I don't really want to add a slider. There we go. 1,000, 1.12. I use Shift 6 to get up to an exponent for my X's. I'm just going to copy that. Loan B just changes this to 24. And loan C, copy and paste is all I'm doing. 306. And now I'm going to go change my settings so I can actually see where this is. So my y-axis, I need it to start, I probably want to see something like -4. But I need to see way up higher because remember, we're borrowing $1,000 and we're going up to $14,000. So I'm going to put it up at $10,000. So I'm putting my y-axis at 10,000. This is what my 3 loans look like. They all start at $1,000. They all show this 0, 1,000 as their starting point. And I can see that the red one is growing slowest because it's the lowest percent of interest. If I want to see where each of these is going to equal $2,000, just remember you can put in a y equals 2,000, and now I can see how long it takes each one. Remember, this is the one that we already wrote down, that it takes somewhere between 2 and 3 years. So 2.6 years is actually what it would be. 2.6 years. A little more than 2.5 years. Loan B, that's my blue one here. Loan B takes 3.2 years. And our loan A takes over 6 years, 6.1 years to double in value. You can see how somebody could really get in financial trouble real quick. All right, be smart with your loans. Lesson 15, you're going to have a chance to work on practice problems 1, 4, 5, and 9. Those are our assigned ones. Thanks, guys.